I hope you're ready to look at some chemical properties. We're going to look at the periodic table and how we see trends in the chemical properties of a number of elements. We will largely focus on period 3 for a number of equations that you need to know. However, we will talk about trends in general as well. So the first thing that we need to point out is this idea of metallic versus non-metallic. Hopefully by now you're familiar with the idea that the majority of elements in the periodic table are metals. We have a small number of metalloids and non-metals. Left-hand side of the periodic table tends to be more metallic. As we move across to the right-hand side, we hit our non-metals, and then we can predict the types of bonding from this. So essentially, a metal is defined by its ease with which it's going to lose its valence electrons. Metals react by losing their valence electron, okay, which means that we can define the idea of metallic character as how metallic something is, because this means that it's really a measure of how easily they lose electrons. Metallic character decreases as we go from left to right across the periodic table, and it increases as we go down a group. Okay, if we think about this, this makes sense, because as we move from left to right across the periodic table, our effective nuclear charge increases, so our electronegativity and all those things that mean that we're holding onto the electrons more tightly to the nucleus increase. So the metallic character is going to decrease because metals want to lose electrons. If the electrons are held more tightly to the nucleus, it's going to be harder to lose them. And in fact, by the time we see non-metals, we're seeing that they don't tend to lose their electrons readily. We see the formation of covalent bonds or anions. So elements such as germanium and silicon display properties of both metals and nonmetals, and they're called metalloids. Silicon will also have particular special semiconductor properties, and the metalloids are used in a number of different things in material chemistry. So just a point to remember that metallic character is all about how readily a metal will give up its electrons. Okay, so the more strongly the electrons are held, the less metallic something will be. One of the other things that we see is melting point variation. In some ways, this should have been in the previous slide when we were talking about physical properties, because melting point is a physical property rather than a chemical property. But with this, we do see some variation as we move across a period. So they're dependent on the structure of the substance, remembering that melting points of metals are dependent on the strength of the metallic lattice. Melting points of ions are dependent on the strength of the interaction between the positive and negative ions. And then the melting points of our non-metals are dependent on the intermolecular forces holding a substance together. So for period 3, as we move from left to right, sodium, magnesium, aluminium, and silicon, okay, we see a general increase in our melting point. Okay, this is because these tend to be metals and metalloids. The strength of the metallic bond becomes stronger with the greater the number of delocalized electrons and the smaller the cation. Okay, so we said that the cations get smaller as we move from left to right. So we get a much higher charge density in our cations and a greater number of delocalized electrons, so our metallic bond strength increases. But as soon as we get out of the metals, we see a sharp decrease in melting point because we hit the non-metals, and therefore we're dependent on intermolecular forces. Silicon has giant covalent. It's very similar to carbon in that way, so it will form giant covalent network lattices. So it has a very high melting point, but then we get phosphorus, sulfur, chlorine, argon. Argon single atoms, very small amounts of dispersion forces. Cl2 is a diatomic molecule, so we've got dispersion forces, sulfur and phosphorus as well. Okay, so the melting point variation is due to the type of bonding that would be exhibited, which is dependent on the type of atom, whether it be metal or non-metal. So this is a summary table of the physical trends: atomic radius, ionization energy, electronegativity, cation and anion radius, and now melting point. Make sure you have a way of putting this in your notes in a way that you understand, that can be summarized and help you remember it. I will give you a periodic table to annotate with each of these trends. So now we move into our chemical properties. Okay, that means that we're going to have symmetrical chemical reactivity down a group. This is because they all have the same valence shell electron configuration, and the way in which an element reacts is dependent on its electron configuration. So in group 1, they all have one valence electron. They're all going to have an effective nuclear charge of +1, so the electrons are not going to be held really tightly. They're metals, so they're going to react readily to remove that electron. Okay, so they have a low ionization energy, they're easily oxidized and form very good reducing agents, terms that will make more sense as we move into redox later this year. But essentially, we have a metal will form a cation plus an electron. This is our ionization energy. Okay, and then they will also reduce water to form hydroxide, forming a strong alkali solution, hence why they are called alkali metals and alkali earth metals for group 2. Okay, we can see here that as we move down the group, the radius increases, which means that, remember, our attraction to the nucleus is distance dependent. So as the radius increases, our electrons are going to be held more, a lot less tightly. So we will see an increase in reactivity. These metals also produce distinctly coloured flames in the form of emission spectra, which we have seen back in ECP. They have low melting points and boiling points because they have a low charge density, so they are quite weak as metals are concerned. The metallic bonds are quite weak. In fact, we can cut sodium with a butter knife. And then they react easily with halogens to form ionic compounds. So we'll get sodium chloride, potassium chloride, and things like that. So the reactivity of metals, okay, increases as we go down a group. Group 1 metals is higher than group 2 because group 1 have a lower effective nuclear charge, so their electrons are held less tightly. So remembering our reactivity, like our reactivity increases down a group because our ionization energy decreases as we go down a group. For the same core charge, we have increasing distance, so the electrons are held less tightly. So we do have some differences, okay? Alkali metals react in similar ways, but they do have different densities, and they do increase in reactivity as we move down the group, with francium being the most reactive because it has the lowest first ionization energy. And then again, we can relate this back to effective nuclear charge and the distance from the nucleus. You can see how our reasoning for this gets very repetitive because it's always based on the same things. For the halogens, we see the opposite trend. This is because they are nonmetals and they react by attracting electrons to them. This is going to be dependent on the electronegativity and electron affinity of these elements because they want to gain electrons. The higher the core effective nuclear charge, then the greater the reactivity of the halogen. So as we go down a group, we reduce electronegativity, we increase distance from the nucleus, so our electrons won't be held as tightly, they won't be as attracted to each other, so our halogen reactivity decreases. Okay, so this is determined by electronegativity, electron affinity, and atomic size. The smaller the atom and the higher the electronegativity, the more reactive the halogen. So this means that reactivity increases up to fluorine, which is our most reactive nonmetal, and then is also increasing as we move from left to right across the periodic table. This is a table that summarizes the reactions of halogens. Essentially what this is saying that a halogen that sits above another halogen on the periodic table will be able to displace the halogen ion and cause it to form the neutral halogen in solution. You saw a similar thing with this, I think, when you did the metallic crystals prac for metallic bonding. But essentially what this is saying is that chlorine, when reacted with bromide ions, is more reactive, so it will steal the electron away from the bromides, forming Br2 and chlorine ions. Okay, because chlorine is more reactive, okay, it will react. If we were to put bromine into chloride, we don't see a reaction because chlorine is more reactive. Bromine is not reactive enough to be able to rip those electrons off the chloride. Okay, but chlorine can remove it from bromine. It can also remove it from iodine because it is more reactive than these. Fluorine would rip the electrons off any of these. Bromine is more reactive than iodine, so it can steal the electrons from iodide to form iodine and bromide. However, iodine is the least reactive, so it's not going to be able to do this. All of the halogens will react with silver nitrate to form precipitates because they are insoluble. Okay, so silver chloride, silver bromide, and silver iodide. We can see an increase in the darkening of the color as we move down from white to a creamy pale yellow into yellow. And this has to do with the strength of those bonds. And remember the excitation of light in these compounds. The other chemical reactions that we need to know is the oxides of period 3. So as we move across period 3, we move from metallic to non-metallic character, and the nature of the oxides forms with these compounds changes as well. Our metallic oxides are going to be ionic in nature, and when they are reacted with water, they will form hydroxides. Aluminium oxide is amphoteric, which means it can react with both acids and bases. And then our non-metals react with water to form acids. They are acidic oxides. Okay? Except for silicon dioxide, which forms a large molecular compound, quartz. Okay, so silica. So as electronegativity increases towards the right, making the atoms better at gaining electrons, this means that we're forming covalent compounds that then react with water. Okay, argon doesn't form any compounds, it's a noble gas. So you need to be able to write the reactions of the oxides with water. Typically, this will be remembering that our sodium oxide is going to form a hydroxide, add water, and balance. Okay. For the case of CO2, this is an oxide of carbon. It will form carbonic acid. Okay, with water and balance. All of these equations are covered in your textbook in the latter pages of chapter 3, so around 110 to 118. You should make sure that you write out all of those equations. They are the kind of thing that you're expected to be able to know. I recommend that you start a new tab on your OneNote notebook, keeping a list of all the important equations so that you can figure out how you're going to learn to write them, the states associated with them, the charges, and being able to balance them. So that's all that we have in terms of our physical and chemical characteristics for the trends. The only ones that we didn't talk about that much are the noble gases. These are the elements in group 18. They were thought to be completely inert. However, they did discover that xenon will react under high pressures and temperatures. So some very extreme conditions. So they stopped referring to them as being completely inert. Now we just refer to them as highly unreactive. The properties of the noble gases all arise from the fact that they have an incredibly stable electron configuration, so they are difficult to remove electrons from, and they also will not accept electrons because they have that complete octet. They are very, very stable, so therefore quite chemically unreactive. And that is it for topic 3. I will leave some worksheets and work for you to do. Hopefully you have a better idea of the immense amount of information that is now available to you in just one periodic table.